Okay, so thank you again for the nice warm welcome here in Spain. My name is Mathis Bloßfeld, and together with Sarrocco, we will convene the first two sessions of this workshop dedicated on terrestrial reference frame computations and precise orbit determination. And the first presentation will be given by Zuheir Altamimi from the IGN in Paris on the ITRF2020 realization. And this will be given remotely, and I hope he is already online and ready to start. Well, that's the second one. Okay. So let's see. Perfect. Hello, Zuheir. Can you hear us?
Okay. Thank you, Mathis, again.
Perfect.
Before I start my presentation, let me, on behalf of the International Association of Geodesy, express my deep appreciation to the representative of the local authorities and the organizers for the ILRS workshop. I am sorry for not being able to be with you in person, but I am definitely missing Spain, missing Guadalajara and Yebes, and missing you all. Back to my presentation, which is about the ITRF2020 and the ILRS contribution in particular. You see the names of my co-authors, the ITRF team. So the key points of my presentation will be the ITRF2020 and its innovation. I will talk about how we model the non-linear station motions. And then I will focus more specifically on the ILRS contribution in terms of quality of the time series that were submitted to the ITRF2020. And in particular, the reference frame parameter, the origin and the scale. And then also another type of element that you need to know is there is a new kinematic model to be used within the ITRF2020. So this slide is a little bit busy, but here you have the table that shows you the input data from the four techniques. From Doris, we have 28 years, 27 years from IGS GNSS, 38 years from ILRS SLR contribution, and from VLBI we have a time span of 41 years. And here you have the number of sites and the theoretical frame origin, center of mass or center of network, etc. Now, this is the map of the ITRF2020. The total number of sites is more than 1,200 sites with an imbalanced distribution between northern and southern hemisphere. We have more than 1,800 stations, and we have a number of discontinuities, which is for me a huge number of discontinuities, more than 3,000, but mostly for GNSS. And this is harmful for the best estimation of station velocities. Okay, how we model the non-linear station motions. Start with the impact of periodic signals. Here I am showing the time series after removing the linear trend for one station located in Brazil and in the Amazon. And as you can expect the nice seasonal signals that we see is due to hydrology. So how we model that? We model that with a sine wave function so that for each station and each frequency, we estimate the coefficient of that sine function A and B. And you can imagine the number of unknowns when we add these, for instance, annual and semi-annual signals for each single station. Now, about the earthquakes, here you see on this map the location of the epicenters, more than about 65 locations. They impacted more than 100 ITRF2020 sites. How we model that, as you see here in this illustration, the original raw data, the time series are in blue, In green is the virtual velocity due to plate tectonics, and the red curve that is imposed over the time series here is what we call the post-seismic deformation. And we model that using 5 functions: logarithmic, exponential, the combination of 2 or 2 exponential or 2 logarithmic. Now, the ITRF2020 new analysis strategy, as shown on this map, you have on this slide, you have the input data. We have more than 253 local tie vectors, but we use, of course, SINX files for these local ties with full variance covariance information. And when we do the combination, we need to add motion constraint at collocation site. So we do data analysis, time series analysis, stacking of the dual technique. We assign discontinuities. We determine the post-seismic parametric models using GNSS data. And then we apply that to all other techniques that are collocated with GNSS at earthquake collocation site. We estimate and remove the first 8 GPS draconitic harmonics. And the novelty in the ITRF2020 is that we accumulated the full 4 technique time series altogether, adding local ties and co-motion constraint. Now, in terms of input, you have the classical output, station positions and velocities, earth orientation parameters, PSD models, and seasonal signals, annual and semi-annual signals expressed in the center of mass of SLR. And in terms of ITRF2020 specification, the origin is inherited from SLR. The scale is determined by a rigorous combination and average of SLR and VLBI, and the orientation is an alignment to the ITRF 2014. Now, in terms of the ILRS quality input data, here I am showing the WRMS of the time series starting in 1993. I just ignored the past Lagius-1 data. And here, as you see, we have an improvement, and compared to ITRF 2014, we have WRMS around 7 to 8 millimeter in horizontal and about 4 to 5 millimeter for the up component, which is probably due to the fact that the ILRS did handle accurately the range biases issues. Now, this slide shows you the ILRS 2020 intrinsic origin and scale. And here, as you see, before 19, for the 3 component of the origin, TX, TY, and TZ. Can you mute your microphone, please? Because I hear some echo. Thank you. Now, we ignored, the data after 1993 when we have the 2 Lagius satellites, it's much more stable, but we still see some discontinuity in the scale time series before 1997.7, and this is probably due to some mismodeling of the range biases that need to be investigated by the ILRS. Now, what about the origin for the ITRF 2020? As I said, it is inherited from SLR long-term center of mass, and I am here redisplaying the 3 origin component TX time series of TX, TY, and TZ. And by comparisons, I am also showing the DORIS TX, TY, TZ. And as you can see, there is no seasonal signals in these origin component for SLR, because we wanted to express the seasonal signals of the stations and avoid absorbing some seasonal motion in these origin component, so that as you can see, we don't see any seasonal signals. But in contrast, you can see here, especially in the Y component for DORIS, significant seasonal signals, which means that there is an inconsistency between SLR and DORIS in terms of seasonal signals. And of course, GNSS frame origin is not reliable, and we can explain why. Now, the ITRF 2020 should be regarded as an augmented parametric reference frame. What does that mean? It means here, the kinematic model, you have the linear part, the usual classical parameters, position at T0 and velocities, and the non-linear part, which is composed of two parts, the post-seismic deformation, and we have refined parametric models as we used more data, and the seasonal signals that are expressed in the center of mass of SLR frame. Now, there is a clear relationship between station seasonal signals, geocenter motion, and the reference frame. And to explain that, I borrowed this illustration from Bloßfeld 2003. Imagine here that you have a load on the North Pole. The stations, the black circles, filled black circles are the station before deformation, and the empty circles are stations after deformation. An ITRF 2020 stations will, it is seasonal signals, will have two components. One is what we call a net translation, which will be equal to all stations, that what we call the geocenter motion, plus a deformation expressed with respect to the center of figure frame. So this is, again, the kinematic model, and the user should be aware of the addition of delta XF, which means the seasonal signal correction for the two frequencies, annual and semi-annual. And we estimated these A and B coefficient for each single station in the center of mass, so that from this illustration, we can write at the seasonal frequencies that the coordinate in the center of mass are equal to the coordinate in the center of figure of the plus the geocenter motion that we also published as a new product for the ITRF 2020. Now, what about the usage of the ITRF 2020 seasonal signals? One of the most motivation of providing the seasonal signals expressed in the center of mass is for precise orbit determination. For that application, our recommendation is to use the CM-based seasonal signals, because it will correspond to the coordinate at the instantaneous center of mass, as that center of mass is the point around which the satellite is orbiting. Now, you can have another application in terms of alignment of global solutions. You can use either center of mass or center of figure seasonal signals, and these have two properties. One is to avoid aliasing the seasonal signals into the similarity transformation, and the second advantage is that the seasonal signals will be accurately retained in the aligned solution. If you use the center of mass seasonal signals, then the translational motion common to all stations, geocenter motion, will be also transferred to the aligned solution. If you use the center of figure, the aligned solution will be free from the seasonal geocenter motion. And for regional or local or regional solutions, we don't recommend using seasonal signals, just because they are spatially correlated and they can have a common mode signal in the aligned solution. Now, regarding the scale, and this will be the last topic that I am discussing here, in the left side, you have SLR and VLBI time series of the scale. In orange, all the VLBI sessions. In red, these sessions that we selected with this condition that the convex hole volume is greater than 10 to the power 19 cubic meter. And what we noticed in the SLR, the VLBI time series of the scale, that there is a drift around 2014, and the IVS is investigating the causes of this drift that we see in the time series. There is another, as I mentioned earlier, an offset in the SLR time series of the scale. So in summary, the ITRF 2020 scale will be the average of the red VLBI and dark blue SLR. And this is the first time in the ITRF history where the scale offset between SLR and VLBI is 0.15 ppb, which means 1 millimeter at the equator. And fortunately, this was expected because SLR provided solutions where they estimated the range biases that has an impact of about 1 ppb. Now you can see in this table the values of the scale at epoch 2015. As you can see in green here for GNSS, we have an offset of about 0.7 ppb with a small drift. And for DORIS, the offset is higher by a factor of 1.4. And this is the reasons why these two techniques were not used in the scale definition of the ITRF 2020. Let me summarize now the ILRS key contribution to the ITRF 2020. We inherit from the SLR the long-term origin, and we access the instantaneous center of mass, which means that it is the origin of the ITRF 2020 seasonal signals. And another contribution is the transfer of an accurate geocenter motion to the three other techniques. And of course, SLR contribute to the scale definition. So this is my conclusion. The ITRF 2020 is a step further in improving the ITRF determination. It adequately model non-linear station motions, post-seismic deformation, and seasonal signals. And as I said before, we are really happy and then thankful to SLR for estimating the range biases, which now bring the scale of SLR closer to VLBI at the 1 millimeter level at the equator. And despite that, we have still see some non-linearities in the scale time series, not only for SLR and VLBI, but also for DORIS. Thank you very much. Should I stop sharing the screen? I am happy to take questions if there are questions.
Can you hear me, Zuheir?
Yes, I hear you.
Perfect. Okay, there's a question by Sergei Rudenko who asks what is the reason of the inconsistency between SLR and DORIS seasonal variations? Do collocating SLR and DORIS stations have the same seasonal terms in the ITRF 2020?
Yeah, all the techniques or collocated station have the same seasonal signal because we constrain them to be equal at collocation site, except for some sites where some stations have different, discrepancies with the other techniques. So basically, they are constrained to have the seasonal signals. Now, regarding SLR and DORIS, I was talking about the origin component where we see seasonal signals, and this means that there is an inconsistency between the two techniques.
Perfect, thank you.
And the reason is not clear to us.
Okay. Any other questions? No? Then thank you, Zuheir, again.